All right, if you're an aspiring engineer or technician, you've got to know about the real unsung heroes of the industrial world. Today, we're going to break down one of the most essential components in pretty much any process plant, the control valve. So let's just dive right in. I want you to picture a massive chemical plant, or maybe an oil refinery. That sprawling maze of pipes, tanks, and reactors. How on earth do they keep all that from descending into total chaos? How is every single variable, from pressure to temperature, managed with such incredible precision? Well, the answer lies in this really elegant, powerful system that is, no exaggeration, the backbone of modern industry. It's called the control loop, and it's what keeps order in all that potential chaos. Now, every single one of these loops has one critical job: to keep an important process variable, like the flow rate of a chemical or the temperature of steam, locked into a very specific operating range. And this isn't just for efficiency. It's absolutely crucial for the quality of the final product and, most importantly, for safety. This diagram here just lays out the entire system perfectly. You can see the high-pressure steam coming in, and there's a sensor measuring the pressure downstream. That measurement gets sent over to a controller, which then tells the control valve what to do. It's this constant, never-ending cycle of measuring, comparing, and correcting to handle any little hiccup in the process. The easiest way to wrap your head around this is with a simple analogy. Think of it like this. The sensor acts as the eyes of the system. It's always watching what's going on. The controller is the brain, doing the math and deciding what needs to happen. And the final control element, which is our star today, serves as the hands, physically going in and making the change. Right, so while the sensor is the eyes and the controller is the brain, it's the hands that are doing all the heavy lifting. And, you guessed it, in most industrial processes, that final control element, the hands of the whole operation, is a valve. And this quote really just drives the point home, doesn't it? Our sources call it the muscle of the process control system. And honestly, that is the perfect description. It's the part that physically gets in there and interacts with the process to carry out what the brain, the controller, decided. So, what is it exactly? Well, put simply, a control valve is basically a super sophisticated automated tap. It gets a signal, and then it precisely adjusts how much it's open. By doing this, it manipulates whatever fluid is flowing through it, could be gas, steam, chemical, you name it, to bring that process variable right back to its target set point. And this is what one looks like out in the wild. This whole assembly, with its two main parts, the valve itself and that big actuator on top, this is what gets installed directly into a pipeline to go to work. Now, to really get how a control valve works, we need to do a little virtual dissection, right? Let's look at the key components that make the whole thing tick. So a complete control valve assembly is made of three really essential parts. You've got the actuator, the valve body, and the internal components, which we call the trim. Each one of these has a very specific, very important job to do. Okay, first up, the actuator. Just think of it as the motor. It takes that corrective signal from the controller, which could be air pressure, an electric signal, or hydraulic fluid, and it converts that signal into the actual physical force and motion needed to operate the valve. And here's a peek inside the most popular type, the pneumatic, spring, and diaphragm actuator. The reason it's so popular is its simplicity and just how dependable it is. See, air pressure from the controller pushes down on that flexible diaphragm. This creates a downward force, it compresses the spring, and that moves the valve stem. It's a really elegant and effective design. Next up is the valve body. This is the main, heavy-duty structure that contains all the pressure. It's the casing that houses all the important internal parts and gives you the connection points to bolt the valve right into the pipeline. And finally, we have the trim. These are the internal components that are doing the real work of controlling the flow. The key parts here are the stem, which gets moved by the actuator, the plug attached to the stem, and the seat. It's the position of that plug relative to the seat that determines exactly how much fluid can get through. Okay, so we know the parts. Now let's get into one of the most important concepts for any engineer who's going to be specifying a valve: how it behaves. The way a valve opens and closes has a direct impact on how it controls the flow. You might just assume that if you open a valve, say 50% of the way, you'd get 50% of the flow, right? But that's not always the case. The relationship between how much the valve has traveled and the flow rate you get out of it is called its flow characteristic, and it's specifically engineered for different kinds of jobs. This graph right here is fundamental for any control systems engineer. I mean it. It shows the three most common inherent flow characteristics. Understanding these curves is absolutely key to picking the right valve for the right job, which is crucial for stable and effective control. First, we've got the quick opening characteristic. And just like the name says, it gives you a huge amount of flow with just a tiny bit of initial movement. It's not great for precise adjustments, but it's perfect for simple on-off jobs or safety relief systems where you need to dump a lot of pressure fast. Next is linear, and this one is very intuitive. If the valve is 50% open, you get 50% of the maximum flow. Simple as that. This direct, predictable relationship makes it perfect for things like controlling the level in a tank or any process where you need a nice, constant gain from your control element. And finally, we have equal percentage, which is the most widely used characteristic of them all. Here, each little bit of stem movement produces an equal percentage change relative to the flow that's already happening. This means it gives you super precise control at low flow rates, but can still react quickly at high flow rates. It's the go-to for pressure control and systems where conditions can vary a lot. So we've covered the what and the how. But where do these amazing components actually make a difference out there in the real world? The short answer is just about everywhere. They're used for regulating the flow of crude oil in a pipeline, making sure chemicals are mixed precisely in reactors, managing steam in power plants, controlling flow in water treatment systems. You get the idea. If a fluid is flowing through an industrial process, there's a really good chance a control valve is in charge of it. By allowing for such precise, automated control, these valves are directly responsible for making countless industries more efficient, safer, and more profitable. And that leaves us with a final thought to chew on. As automation, smart sensors, and Industry 4.0 keep advancing, how will this essential muscle of the control loop get even smarter and more integrated in the future?